All right, everybody. Good afternoon. So last time we talked about equality constraints, solving optimization problems with equality constraints. I have a question about the homework. I'll talk about the homework towards the end of the lecture, but let me now just get immediately to lecture 4. So today I'm going to talk about the variational approach. So the variational approach is similar to what we did in solving the optimization problem with constraints, or solving the optimization problem in general, which is to rely on perturbation. We will perturb the optimal point and the optimal trajectory a little bit by epsilon. And that perturbation, to do the perturbation, we can then follow the Taylor series expansion, and we can ignore the higher order terms. So it's an approximate solution. It's not exactly 100% precise solution, but it's good enough. Why it's an approximate solution? Because we are assuming that the perturbation is small. So as long as we are near the optimal point, then this is a good solution. Okay, so I'll explain what I mean later on. But so we are going to apply the variational approach to solve this problem: fixed time, free endpoint problem. So let me see here. Yeah, so this problem, we have a system described by a differential equation, and we want to minimize the cost function. We have a penalty on the final state, and we have also another penalty in terms of an integration on the states and the input of the system. We are given the initial conditions. We are also given T1, so we need to solve this optimization problem in fixed time, and we don't care about the final state. So what is the U that minimizes that cost function? So here's a motivational example of like an application that describes this problem. All right, so let's consider an energy-aware drone navigation. So let's say that we would like to design a control system for an autonomous drone. We would like to deploy the drone in the field. Typically, this is a military application, but also, this application can be found in security purposes in general, even commercial security, and also for surveying geographical areas. So, they are also known as reconnaissance or surveying scenarios. So basically, we have a quadrotor drone. This drone must operate for a fixed mission duration, capital T, seconds. The drone should fly smoothly and avoid aggressive maneuvers, right? For practical reasons, military reasons. Of course, we need to minimize the energy consumption, okay? And at the end of the mission, the drone does not need to be at a specific location, okay? However, we prefer it to end in a stable, low velocity condition. So these are the constraints. These are the operational constraints on the drone in the field, right? So we wanted to hover around a geographical area. Presumably there is a camera. The drone is equipped with a camera. And so there is no aggressive maneuvers or anything like that, okay? So just hover smoothly. We want to minimize the energy consumption. So, and at the end of the mission, the drone does not need to be at a specific location, okay? But there are some preference here regarding the the final state of the drone. I'm going now next in the next slide. I'm going to translate all these constraints into mathematics. This is key, right? This is what we would like to get practice on. We would like to translate these conditions into mathematics, into problem statement. But this is basically an optimal control problem with a free terminal state and terminal penalty. So this is our first job. Our first job is to determine what type of problem is this. Okay, what type of problem is this? So this is an optimal problem with free terminal state. Why it's free terminal state? Because we don't want the final state to be specifically something, okay? But we want to put like a constraint on it, okay? And yeah, so that's the idea. So, okay. So please stop me at any time if you have any question, okay? So let's start by defining the states of the system. So let the state include the position and velocity of the drone. Okay, so P is the position of the drone at any time, and V is the velocity. It's a quadrotor drone, so we are going to assume that there are 3 motors. And so the drone has 3 motors, okay? Which means that the drone will have 3 U's, right? This is the control input, which is basically the acceleration or thrust command. So because we have 3 thrusts, so 3 U's, right? Each U would have its position and velocity, okay? So a simplified, this is like as simple as it gets, model for the drone is that the derivative of the position is equal to the velocity, the derivative of the velocity is equal to the acceleration, and that's exactly what the input is. Okay, so the thrust will give like acceleration to the drone. So this is like at each of the 3 motors, you have P dot is equal to V, V dot is equal to U, right? So you can put them all in one vector. P1, P2, P3 is equal to, or P dot, P1 dot, P2 dot, P3 dot is equal to V1, V2, V3, and V1 dot is equal to U1, V2 dot is equal to U2, and V3 dot is equal to U3. We can then put them in a compact form in the form of X is equal to F, a function of X, U, and T. And we are going to assume that because we are the operators of the drone, we know what are the initial conditions, what are the initial positions and velocity of the drone, and what's T0, right? X here is a vector that contains all the states. So X is this one here, is this vector here. Okay, so this is the mathematical model. There could be other more complicated, more complex mathematical models for the drone, but this is like to make it simple. Okay. All right. So we want smooth and energy efficient flight. That's what we want. So we want to penalize a deviation from the stable flight, right? State cost. So we need to put a cost on the state, and we want energy minimizations, right? So we want to make U as small as possible, because if U is as small as possible, then it's not going to use as much fuel so we need to, if we minimize U, we are going to minimize the fuel. All right, so to make the state smooth and stable, right? This is the typical cost that we can choose, X transpose QX, right? And to make U as small as possible, this is the typical. It's not the only choice, it's the typical choice, and that choice it has many advantages. But this term here, U transpose RU, minimizes the energy, X transpose QX, smoothes X, makes X smooth, doesn't have like sharp transitions, and also guarantees that X is stable, right? It doesn't go out of bound, right? So there are two terms there, right? These two terms, if you see here, if you notice, they are quadratic terms. We call them quadratic terms. X transpose QX. Remember, X is a vector here, and Q is a matrix, R is a matrix. These are quadratic terms. Quadratic terms have many advantages in terms of differentiation, positive definiteness, and all that. Okay, so it's deliberate. That choice is deliberate, and it's typical. It's typical, and and typically when you solve optimization, like if you want to solve uh, for U star for the optimal U, the U will be linear because of this choice. The form of U that we'll get later on is of a linear form. Okay. Okay, so this is the choice that will satisfy these two penalties, which are requirements for the problem, right? We want smooth X with a stable flight, and we want a minimum energy. This will satisfy the minimum energy requirement. This will satisfy the stable, smooth trajectory of X. Okay. Now, for this problem to be solvable and to guarantee controllability and stability, R, this matrix R, needs to be positive definite. It has to be positive definite. Okay. Sorry. Yep. So R needs to be positive definite, and Q needs to be positive semi-definite. Q can be positive semi-definite. And one caveat that I need to mention here is that the fact that Q can be positive semi-definite doesn't necessarily mean Q is zero. The matrix, the whole Q is zero. Does not necessarily mean that. Okay, so keep that in mind. Okay, so anyway, these are technical points. Maybe we can consider them later on in the course. But this is the choice. Okay. Okay. Now the drone. So there is also another constraint on the terminal state of the trajectory. We are not required to land or to position the drone in any specific point. So there is we don't need to solve for U that will drive X to a specific X. Okay? There is nothing like that. However, right, there is terminal penalty, which is the drone does not need to end it. We need to prefer, or we prefer a nice final condition. Nice final condition, right? And if you go read here, we need the final like position P and V, right, to be stable and low velocity condition, with a low velocity condition. Okay. So to satisfy this statement, we can choose the final penalty to be at T1, which is the final time, X at T1 transpose S X at T1, where S is positive semi-definite matrix. That will make X at T1, which is the final state, you know, at final time, is smooth, right? But X at T1 could be anything. X at T1 could be anything, right? We want it to be smooth, to be like stable and smooth and nothing crazy, okay? And this also will guarantee that it's going to be as small as possible in terms of magnitude, in terms of P and V. Putting everything together, right? This is the cost function. This is the control problem that we need to solve, right? So L, which is this one here, right? That guarantees stability, smoothness, and minimum energy, right? We put it under the curve, like the integration from T0 to T1, L, right? And we have a penalty on the final state. right? This is the penalty on the final state. Putting everything together, that's the cost function. And the problem is find the optimal control that will minimize this cost function. Subject to, of course, the system dynamics and the initial state. And knowing that T1 is given, it's fixed, X of T1 is free, and U is unconstrained. Right? We can choose any U we want. So there are no constraints on U, right? So this is the control problem. Okay, yeah, I just showed you now a motivational like application for that. Okay. So now the problem is, or the question is, what is U that will solve this problem? What is the optimal control? How can we get it? How can we derive an optimal control that will solve this problem? All right. So before we dive into the solution, the derivation of the solution, right? Of course, we can generalize this, right? And we can this problem can be seen in many applications: model predictive control, energy efficient robotics and drones, reinforcement learning with terminal rewards, right? And systems that must behave well but do not have strict end state target, right? All these fall into or fall under this problem formulation. Right? So the key idea here, this is the key idea, is that we want to guide the final behavior of the system using a terminal cost instead of a hard constraint. We want the position and velocity to be, let's say, 5 meters and 6 meters per second, for example. We don't want that. It's not that, right? So it's not a hard constraint on, most likely we'll consider that problem later on in the course, but for now, it's just a terminal cost, but not hard constraint on the final state. Okay? That's the key distinctive feature of this problem. And of course, in addition to T1, the period is fixed. The period of optimization is fixed. Any question up to this point? Yes.
The formula for L.
Say that again.
Formula for L
yes.
equation. Yeah, it's similar to the LQR.
Yes, exactly similar.
Same?
It's the same. It's the same.
Same concept.
It's the same thing. Yes. So for LQR, right? We have exactly the same two terms. One to guarantee stability, smoothness of the state. The other one minimizes the cost function. What's the difference with? We'll talk about LQR later. But what's the difference with LQR? The difference with LQR, T1 is infinity. Okay, so you have infinite horizon to do the optimization. Typically, this is optional. We could have it. We don't. Typically, we don't have it. We don't have any cost on the final state in LQR. Okay, but that's the difference with it. But LQR can be a special case of this one. That's to your point. LQR is a special case of this. LQR is linear quadratic regulator, the most common optimal controller for linear systems, right? The most popular optimal controller for linear systems is linear LQR, right? It's a special case of this one. Thank you for this question. It's an excellent question. It's a special case of this problem where T1 is infinity, right? And it's for linear systems, which means that another difference is that notice that the dynamics here can be, the way I'm writing it, it's general F, and which means it includes nonlinear systems. So this problem includes nonlinear systems. For LQR, it's a linear quadratic regulator. The dynamics of the system are assumed to be linear. Okay, so everything is linear, everything is nice there. Okay, but in this problem here, the system can be modeled through or via nonlinear dynamics, nonlinear equation. Okay, so this is why this is a more general problem than the LQR. LQR is a special case of this problem. Okay. Yes, go ahead.
So in this problem, it features a terminal cost. So what if we didn't have a terminal cost for the
It's okay. You could have it 0. So you could have this one 0.
Okay.
Yeah, no problem. Which means that you don't have any terminal cost. You don't care about the final state of the drone. Doesn't matter.
Gotcha.
Yeah. Any other question? Okay. We move on. Okay, let's step by step, let's try to come up with solve the problem basically. So derivation of the necessary condition. Let U star. So in this course, typically when I use a star, it means the optimal solution, the minimal, okay? The solution or optimal, which includes minimal or maximum solution. But typically it's minimal. We're talking about minimum solution here. Let U star be the optimal control, which means that if you take that U star, plug it in the cost that's based on the U star is less than or equal to the cost using any other U, okay? For all U, right? So this symbol here means for all U, okay? Let X star be the corresponding optimal trajectory of, so you take X star, you take U star, plug it in or apply to the system, right? The system will evolve according to this differential equation. X star dot is equal to function of X star U star T and with initial condition. Okay? Now let's start the variational approach. The variational approach, we are going to like what we did last time, we are going to perturb the trajectories. Okay? Because U is a vector, this is how I'm going to perturb it. Okay? So I'm going to perturb it by another vector eta, right? Multiplied by a parameter epsilon, where epsilon is a scalar parameter, right? With a magnitude sufficiently small magnitude. Right? Hence, we have like a perturbation. We're perturbing that vector by a small amount to the left or right, meaning epsilon can be positive or negative in this case here. Okay? So it's a well-known fact in mathematics that says by continuous dependence of the solutions of the ordinary differential equation on the right-hand side functions, right? So we're talking about this equation here. Okay? So the derivative continuously depends on the right-hand side, right? So the right-hand side is a continuous function. In other words, right? If we are assuming that f is a continuous function, because of this setting, right? A small perturbation in U from U star will produce a small perturbation in X from X star. This is a well-known fact for continuous functions of this form here, continuous equation of that form, right? So essentially what I'm saying here is that because we are going to perturb U star, okay, if we take that U, plug it into the system, X will be perturbed by approximately the same amount. That's what because of continuity of the functions, because of the continuous property of the system, okay? So, which means that we can write X as X star, the optimal X, plus epsilon, the small parameter here, times vector phi, right? Vector phi. So basically, it's not the same as eta, but it doesn't matter, right? Because we call it an order of epsilon. This term here is an order of epsilon. It gets smaller as epsilon gets smaller, right? That's the idea here. Okay, so this is the setup. Okay, so this is the variational approach setup. Okay, we perturb U. We perturb U star. And that perturbation will induce perturbation in the state. Okay. Okay. Now let's linearize around that perturbation. So you have U star, and then we have X star. We are now operating near the U star and X star. Okay, we are going now to linearize in that region around X star and U star. So substitute the perturbed variables into the dynamics. Okay, so what that means is take this, substitute it back in the dynamics, which means that differentiate this right-hand side, right? So if you differentiate the right-hand side, this is what you get, right? And substitute back, so you have X dot is equal to f of X plus, not plus, and U and T, right? So replace X by X star plus epsilon phi, differentiate, you get that. F, replace X by this, and U by that, okay, and T, okay? So we have that. Now, expand in Taylor series about epsilon is equal to 0. So basically, what we are saying here is linearize around epsilon is equal to 0. So remember, when epsilon is equal to 0, essentially we are at the optimal point, right? So we want to come up with a linear model near the optimal point. That's what we want, right? So so Taylor series expansion of the right-hand side, right, is equal to the function at epsilon is equal to 0 plus epsilon times the derivative of f with respect to epsilon. Okay, so if you use the chain rule, for f, right? So you have df over dx times dv. So this is df over. This should be df over dt. Okay, so you have df over dx times. 1 second. Let's see here. No, this is the gradient. Yeah, you take the gradient times p plus the gradient with respect to u times eta times epsilon plus higher order terms times epsilon, right? So plus second derivative of f with respect to dx squared, so on. So there are higher, we call them higher order derivatives, and because they are all multiplied by epsilon, actually epsilon squared and epsilon cube and all that. So we are going to call these order of epsilon. We have a property that we talked about in a previous lecture that is order of epsilon over epsilon, and you let epsilon go to 0, right? That's equal to 0. So this is an order, this is a property. I did not give you the proof of that, but it can be shown that order of epsilon over epsilon, when you take the limit of epsilon go to 0, that term will go to 0, okay? Now, when you subtract the nominal equation, right, you will end up with d phi dot is equal, epsilon phi dot is equal to epsilon equal to this term plus order of epsilon, okay? So basically, you take this, subtract, take this to the other side with the minus, right? And that will be equal to epsilon phi dot. Why? Because this part here is this term here, this function is x dot star. Okay, so by definition, right? Yeah, so this is that, right? So if you take it to the other side, right, and you substitute this here, right, this will go with that, and you will end up with epsilon phi dot, okay, is equal to that plus order of epsilon. Divide by epsilon both sides, right, and let epsilon go to 0, right? You will end up with epsilon would go away from here, and for a sufficiently small epsilon, order of epsilon over epsilon is equal to 0. This is why that term will go away, will vanish. Okay, so we'll end up with this one here, and Also, phi at t naught is equal to 0. So this is differential equation in terms of phi, by the way. Okay, so keep that in mind, right? Any differential equation, it needs boundary conditions. The boundary condition for this differential equation is that phi of t naught is equal to 0. How do we know that? If you plug in t naught here in this equation, okay, t naught in this equation. So what you'll end up with is x of t naught is equal to x star of t naught, which is given as x naught. So x at t naught is, go back, is x naught. Okay, so we have x naught here, x naught here. This will go away with that one. You end up with epsilon of phi of t naught is equal to 0. Hence, and epsilon is not 0, right? Epsilon is a small parameter. Hence, phi of t naught is equal to 0, right? So this is the boundary condition for this equation. Okay, so let's continue. Now, this is the key to the solution, right? This slide is very important, right? It's the introduction of the co-state. Remember the Lagrangian multiplier, right? And Lagrangian in last lecture. This is similar to that. Okay, this is similar to that. So we call that the co-state. It's a similar idea to the Lagrangian multiplier. Let P of t be an n-dimensional function of time called the co-state. So we're going to call this the co-state. Right? Now, insert the identity, right? So why this is an identity, the integration of P transpose times F minus X dot is equal to 0, because obviously this is equal to 0, right? X dot is equal to F of X. So obviously this is why we call this identity, okay? Just 0, okay? But okay, now we are going to add this identity to the cost function, okay? So we are going to add this to the cost function. This is the cost function, right? In the cost function, we have L, nothing. So we are going to insert that here. Insert that here. Okay. Now define the Hamiltonian. Hamiltonian is actually one of the principles of this course, right? This is basically, we are going to define the Hamiltonian function as whatever is as this one here, L plus P transpose F, this positive term here. Okay, that's the Hamiltonian. So the cost function will be terminal cost plus integration from T naught to T1 H minus P transpose X dot. Okay, so in this slide, we didn't do nothing. We basically, we played with this 0 identity, right? And we introduced this co-state, which is P, and the Hamiltonian, which is H. You'll see now how we are going to use these two terms, or two, these two terms to solve the problem. Any question up to this point? Okay, so now now we're going to do the first variation of the cost. Okay, we are going to so here up to this point we perturbed the solution, the U star and X star. Now we are going to perturb the cost. So we are going to expand the penalty. Remember, the penalty is a nonlinear function. K here is a nonlinear function of the final state, right? So any nonlinear function, I can express it using Taylor series expansion, right? This is the key here. So I'm going to perturb it around the optimal point. So so which is at epsilon. Remember, epsilon is equal to 0 is the optimal point. Then we are at the optimal point, right? So Taylor series expansion of k is equal to k evaluated at x star of t1 plus epsilon dk over dx phi of t1 plus order of epsilon, right? Higher order terms. Okay. Now, if you do the integration of parts by parts from t naught to t1, p transpose x dot is equal to p transpose x from t naught to t minus integration from t naught to t1 p dot transpose x with respect to t. So like a simple, straightforward integration by parts, you'll arrive at this point. Okay, so I'm going to miss a couple of steps here, and just because I don't want to spend much time on mathematical derivation. Okay. But anyone who's struggling to see the next steps, let me know, okay? But basically what I'm going to do is, we perturbed, so what we are going to do is we are going to subtract optimal from perturbed cost, right? So I skipped the derivation of the perturbed cost, the final derivation. But basically, if you take JU minus JU star, take it from me, okay, for now. Just trust me when I say that this is what you will get, okay? Epsilon dk over dx. When I use this symbol here, it means the derivative evaluated at the optimal cost. Right? So for example, let's say that k is equal to half x squared. Then dk over dx is x. Evaluated at x star, so it's x star. Okay, this is what it means. When I use this, it means do this and then evaluate it at x star. Okay, so plus the integral from t naught to t, partial of Hamiltonian with respect to x, evaluated at the optimal point, times phi, plus partial h with respect to partial u, evaluated at the optimal point eta. Okay, plus epsilon p transpose t1 phi t1, plus epsilon integral from t naught to t1 p dot phi plus order of epsilon. Now, okay, I know that this is ugly for now, that's okay, okay? But the point here, why we are doing this is because U star is the optimal, JU, the cost at U minus the cost at JU star is larger than or equal to 0. Okay? By definition of the optimal U, okay? We want, and this is the key here, we want to find U that will make this right-hand side is equal to 0. That's what we are after, right? We are after U, which is equal to U star in this case, right? So when U is equal to U star, then the right-hand side will be equal to 0. Okay, that's the idea. So we have that, right? And this is the key. So basically, if you look at these terms, all these terms are multiplied by epsilon, right? And remember, epsilon is a small parameter that can be positive or negative, but with a small magnitude, okay? So our only hope to minimize this, which meaning equated to 0, and hence we have our U that is equal to U star. Our only hope, right, is that all the terms that are multiplied by epsilon are equal to 0. This is the only hope, right? So this is why you take epsilon as a common factor, okay? And then you equate all the terms equal to 0. So if you take epsilon as a common factor, and then, for example, take P of T1 as a common factor from here and here, you end up with this, and take phi as common factor from here and here, you get that term, and then you have that term that's there. Okay, so all that must be equal to 0 to solve the problem. Okay, so that's good. That's good, right? But and where does U show up? U shows up here. U can show up anywhere, actually, right? You will see later in right now we are talking in general, right? But you should show up in this equation because of the setup of the problem. You will show up, right? But also there is another unknown in this equation, which is P, the costate. So in this equation, right, we have two unknowns. We have U and we have P. Okay, so we need to solve for U and P. And you'll see in an example what I mean by that. Okay, so this is the general setup of the problem. So first, choose P to satisfy P dot is equal to minus the partial derivative of the Hamiltonian with respect to X at the optimal point. Why? Because of the definition of the Hamiltonian. Look at the definition of the Hamiltonian. The definition of the Hamiltonian, right? Um, no, not the definition. I misspoke. I'm sorry. I misspoke. Let me take a step back, one step back. As I mentioned, our only hope for this to be equal to 0, to minimize this term must be equal to 0, which is the coefficient of epsilon, right? So now look at this term by term. This one, and that one. Okay? Let's look here. Let's look here. Right? For this term to be equal to 0, right? P dot, we need to choose P dot to equal to minus this. That will take care of that term. That will make it 0. Okay? So that's number one. Number two, we need to choose P transpose of T1 at T1 or P at T1 to be equal to the transpose of this. That will take care of that term. That will make that term is equal to 0. Okay? And then what's remaining is that term. That term must be equal to 0. Right? That term, what's that term? That's the partial derivative of the Hamiltonian with respect to U times eta is equal to 0. Okay, so now we end up with three conditions for this term to be equal to 0. Okay, let's translate these conditions into practical conditions. In order to do that, first of all, let me give you this lemma here. This lemma is lemma 5.2 in the book, and the proof is in the book. So what does this lemma say? It says that let H be any piecewise continuous function on a domain. Okay, and let's say that we have the integral from T0 over T1 over that domain of that function times another function, another piecewise continuous function alpha, right? Any or all piecewise continuous alphas is equal to 0. So let's say we have that, okay? Then it's a proven lemma in mathematics that H is going to be equal to 0 on the domain. That H is going to be equal to 0 in the domain. Okay? So if you apply that lemma here, right? If you apply that lemma here, so we have the partial derivative of H over du over U evaluated at X star times eta is equal to 0, right? Then in that case, we know that eta is a piecewise continuous function of time, not necessarily equal to 0, right? Then in that case, based on this lemma, this must be equal to 0, right? This function here must be equal to 0. When evaluated at star, it gives you, this is how we write it, right? So we can write it this way, or we can write it that way, where the argument here is X star, P star, U star. Okay, so both are the same. Okay, so this is a translation, based on using this lemma, a translation of this one here. Okay. Okay. Now we have arrived at the solution of the problem, and let me summarize. Let me show you how what does that mean, right? Or a summary of the necessary conditions. So in order for U star to be optimal, right, it's necessary that there exists a co-state P star such that X star P star is a solution to the 2-point boundary value problem. Why this is called a 2-point boundary value problem? Can anybody tell me why this is a 2-point boundary value problem? Maybe I'll jump here just for saving time. Because X star satisfies X star dot is equal to a function of X star plus, not plus, with the initial condition. X at T naught, X star at T naught is X naught. That's one boundary value problem. The other boundary value problem is this differential equation with this boundary condition. So we have two ODEs with two boundary conditions. Hence the name 2-point boundary problem, right? Two ODEs with two boundary conditions, it is well known that they can be solved together. And this is exactly what's going on here, okay? So we solve the problem in a way, we are going to solve the problem through the solution of two coupled ODE problems with two boundary conditions. This is the key, okay? And you will see that in the example that I'll show you later. But this is basically how, this is the benefit of adding the co-state, right? It adds one ODE with one boundary condition, so you end up with two boundary conditions that you could solve for U star. All right, so first one is X star dot, right? Satisfies, of course, is equal to f of X star U star T, but also it is the gradient of the Hamiltonian with respect to P, right? Because if you go back to the Hamiltonian, right, if you differentiate H with respect to P, you end up with F, and that's X, right? So if you differentiate with respect to P star, you end up with X star. So that's that. That's that, okay? Now P star, right? So P star is the negative of the gradient of the Hamiltonian with respect to X. The negative of the Hamiltonian with respect to X. Let's see how that happens. So that's that. That comes from here. So that comes from here, right? It's P star is the negative of the gradient of the Hamiltonian with respect to X. All right, that's that. And of course, when you take the gradient of the Hamiltonian, that is times minus, so you have minus the gradient of L with respect to X minus df over dx, which is also the gradient here, times P evaluated at X star, right? Where did we get this? We get it from differentiating the Hamiltonian with respect to X. You multiply by negative, right? You have that, differentiate that with respect to X, differentiate that with respect to X. Remember, P does not depend on X, okay? So we have that, okay? The boundary condition for this one, for this equation, we know it, it's X naught, that's given, right? The boundary condition for this one, we get it from here, from this one. This is the boundary condition. It's just a terminal condition. It's about, you know, an ODE, right, needs a boundary condition. It doesn't matter whether it's the initial time or the final time, as long as it's a boundary condition, okay? So here we have the final time. So it's P at T1 is equal to the gradient or the partial of K, the penalty, the final penalty, or with respect to X, evaluated at X star. right? So you have P star of T1 is equal to partial K over partial X evaluated at X star T1. Okay? And last one is, we get it from here, this condition, which is the derivative of H, or the partial derivative of the Hamiltonian with respect to U must be equal to 0, right? Which makes sense, by the way. This on its own makes sense, right? Why? Because if you look at the Hamiltonian, right, what do we want? We want to minimize the Hamiltonian, right, with respect to U. So remember, U let me I don't want to risk confusing you, so maybe I'll stop. I don't want to say that. Okay, anyway, so these are the necessary conditions. These are the necessary conditions that solve the problem. Let's now, in the remaining time, let me apply this or these conditions to solve a problem. Okay? So here's the problem. Consider a first order system, nonlinear system. Right? So this is a nonlinear system. Okay? X dot is equal to minus X minus third X cubed plus U with initial condition. So the initial condition X naught is given. Okay? It's first order, so it's a scalar. Dimension is 1. We are not dealing with vectors here. We're dealing with scalars. Okay? The cost function is half x1 squared plus half integration from 0 to 1 x squared plus u squared. So we don't need the transpose and all that, right? Because everything is a scalar. Okay? So we have that. So what is the optimal control that will solve this problem? Okay? This problem is finite time problem. As soon as you see finite time problem, right, with a final penalty, then this is the free final state optimal control problem. Okay, but this is the key feature. One here, finite time, and we have a final penalty there. Okay, terminal penalty. Okay, so just to relate this to the terminology that I used in the previous slides, F is the right-hand side of this equation. L is whatever inside the integration, right? Multiplied by half, right? So remember, L is not only that multiplied by half, and K is the function K is half X squared. That's what it is, okay? So, okay, first thing we need to do is, to solve this problem, is to define the Hamiltonian. So the Hamiltonian is equal to L plus P transpose F, because everything is a scalar, I don't need the transpose. So you have L plus PF. So that's L plus PF. We are good there, right? And in this case, I'm going to start with the last condition and take my way back, okay? Because I want to, so take the derivative of the Hamiltonian with respect to U and equate it to 0, right? So if you differentiate with respect to U, you'll end up with U from here plus P from here. That's the only term, PU. So if you differentiate it with respect to U, you'll end up with P. So you have U plus P is equal to 0, or U star. We're solving for U star here, okay? So these all these conditions, all these 4 conditions are at the optimal point, at X star, P star. Okay, so from there you can see that, okay, we have a formula now for U star. It's equal to minus P. The only problem is we don't know what P is. Okay, so we need to solve for P. But it's a starting point. Okay. The state, you have X dot star is equal to minus X minus third X cubed plus U. Substitute by U, right? The U star here minus P. So you'll end up with that. So here, I could have used star here and here. Yeah, that's fine. Everything it should be in star in this slide, okay? The co-state, right? So the co-state is the negative of the gradient of the Hamiltonian with respect to x. Okay, so which means that take the Hamiltonian, differentiate with respect to x, multiplied by minus. So you end up with minus x from here, plus p from here, plus x squared from there, from this one here, right? So that's, yeah, so you'll end up with minus x plus px squared. Okay, take minus as a common factor. So you end up with everything should be in terms of p star on the right hand side. Okay, so you have p dot star is equal to minus k minus p star x squared. Okay, this is why I mentioned 2-point boundary problem, which means two coupled ODEs with two boundary conditions. This is one ODE with x at t naught is equal to x naught. And this is the second one, we need its boundary condition. Now, the boundary condition comes from this condition here. You take k differentiated with respect to x, evaluate at x star t1. Okay, there's no transpose because it's just one scalar, right? So what is k here? K is half x squared differentiated with respect to x. So you end up with just x, and then evaluated at x at t1. So it's just x at t1, which is just 1, x at 1, right? Remember the time is from 1, so t1 is 1 in this case here. Okay, so it's x at 1. Okay, that's it. That's it, right? So these are the boundary conditions. This one is for this equation. This one is for that equation. Two ODEs, coupled ODEs with two boundary conditions. And you solve it, you end up with the optimal x star, the optimal p, that will give you the optimal u star. You take that u star, you apply to the system, the drone or whatever, it will do exactly as it's supposed to do. Okay? That is the problem, and that's the solution. Of course, as you can see, it requires a solution of two coupled ODEs, right? Which is not always easy, especially if these ODEs are nonlinear ODEs, as in this case here, right? So it's not always easy, and especially if you have, this is like first order, you know, if you have second order, third order, and so on, so it's not easy, and especially if you want it in a closed form, right? There are many algorithms that do this in a recursive way, right? But this is going to be a theme of this course here, that especially when we, for linear systems, everything is nice. You can come up with a closed form solution and everything. When we deal with nonlinear optimal control problems or linear time varying problems, then the solution will become not easy, right? Or computationally speaking, not easy, okay? But anyway, now with the advancement in computational capabilities, it's now becoming more and more efficient to solve these problems. And remember, this problem is solved under the assumption that we know the model of the system, right? When it comes to reinforcement learning, right? Reinforcement learning solves that problem precisely by relaxing that condition, that we know the mathematical model of the system, right? So it replaces the dependence of the mathematical model of the system by data, right? So reinforcement learning uses data, but basically it follows like similar approach to this one here. Any question? Right, so maybe I have 3 minutes. So let me very quickly, I have a question, I believe it's from Henry here about the problem 2. So let me, yeah, you wanna say, yeah.
I think I figured it out.
You did?
Yeah.
Yeah, okay. So, but anyway, let me just say in general for the benefit of everyone. Yeah. So let me just quickly share my screen. So, okay, very quickly here. Okay. Okay, so the first one is straightforward. The second one, I added C and D and E to complement what we did in lecture, okay? And D says that geometrically, explain geometrically why the gradient of F as the solution must be parallel to the gradient of the constraint. So geometrically means analytically, like loosely speaking, right? Using equations show that the gradient of F, right, is parallel to the gradient of the constraint. Right, so basically, one way to do it is you define the Lagrangian equation, F plus rho transpose G, right? And then equate it to 0, differentiate, take the gradient, equate it to 0. You will see that the gradient of F is equal to minus the Lagrangian multiplier times the gradient of G, right? So you can see that the gradient of F is parallel to the gradient C, and you can verify it at the optimal point. So if you substitute at the optimal point, you'll see that the left-hand side is equal to the right. That's all what I want you to show in this equation. Okay. Is there any other comment quickly about any question about your homework I can address? Okay, let me know. We have office hours tomorrow and Thursday. Let me know if you have any question. Okay. Thank you very much, guys, and see you next time.